Welcome to our afternoon session on geoengineering. I'd just like to remind all the speakers the total time will be 12 minutes for each talk, which means the red light will come on after 10 minutes, so we have time for a question or two. Our first speaker is Ben Kravitz.
Hi, everyone. So I'm going to be talking about the climate model response from the Geoengineering Model Intercomparison Project, or GeoMIP. And I'd first like to thank all of my many co-authors who are all listed here. So I should first tell you what GeoMIP is, in case you haven't heard of it. What we wanted to do is get climate modeling centers from all over the world to do the same geoengineering experiments so that we could figure out robust features of the climate model response. So we have 4 core simulations in GeoMIP right now. We're working on more. They involve counteracting radiative forcing from CO2 increases with a shortwave reduction. So 2 of the experiments involve turning down the sun to balance CO2, and 2 of the experiments involve putting sulfate aerosols in the stratosphere, similar to how a volcanic eruption cools the climate. And as of right now, we have output from 12 climate modeling groups from 9 different countries. And if you're interested in GeoMIP, we have a website, and I'll put that link up later in case you need it. So, of the 4 core experiments, in this work, I'm calculating only on experiment G1. So, from a pre-industrial control, you instantaneously quadruple CO2, and you also turn down the sun, so you get a net balance in top of atmosphere radiative forcing. Now, this is highly idealized. This is not how geoengineering would be done in the real world. But the advantage of this one, as opposed to, say, the other ones with transient greenhouse gas simulations or more realistic sulfate aerosols, is that everybody can do this one, and we get a really good signal-to-noise ratio. So this lends itself really well to model intercomparisons. So, how about some results? This one is differences in surface air temperature, and I'll just go through the little caveats here as to what I'm actually plotting. So this is the all-model ensemble average, all 12 models averaged together, for experiment G1 minus the pre-industrial control, and then I averaged over the last 40 years of simulation. There are 50 years in total. I threw out the first 10. And stippling on all of these plots denotes agreement on the sign of the anomaly for at least 75% of the models. For this particular plot, it's 9 out of 12. So what you can see from this figure is, in very broad brushstroke terms, geoengineering overcools the tropics and undercools the poles. And the dominant reason for this is radiative. So CO2 has a relatively uniform radiative forcing distribution. It warms pretty much everywhere. But the solar radiation has a distinctly latitude-dependent distribution. So while you might end up balancing globally averaged radiation, you end up decreasing the equator to pole temperature gradient. And this imbalance is actually stronger in the winter pole than the summer. You get more warming in the winter pole than the summer. There's a seasonal variation. And that's because if you're turning down the sun over the winter pole, well, there's no sunlight, so anything times 0 is still 0. Now, I do want to mention the stippling a little bit. The stippling convention is different from what's used in the IPCC reports. And the reason for that is because it's basically because of our experiment design. So by the way the experiments are designed, we basically balance globally average temperature, and so that reduces temperature-related feedbacks, which are some of the source for any nonlinearities that might result in model difference. So we do get a lot of model agreement. That's not necessarily that we get more or less agreement than the IPCC models, but we get it for different reasons than, say, future climate scenarios. So we wanted to distinguish that. Now look at hydrology. We chose to look at precipitation minus evaporation. A lot of people have looked at precipitation only. The reason we chose this is we wanted to get closer to the idea of whether it's getting wetter or drier. We should also look at soil moisture. I haven't done that yet, but this is one step. And what you can see, so there is a lot of coloring on here, but over 83% of the globe and 89% of the land surface, the P-E anomalies are less than 0.2 millimeters per day on average. So not really a lot to write home about for these. But where you do get changes are here in the tropics. And a lot of these are manifested as precipitation reductions. And one of the reasons for this was, I think, really nailed by Bala et al., where CO2 warms the troposphere, but if you reduce the sun, it tends to cool the surface more than the troposphere, more than the middle troposphere, and you actually end up changing the static stability. And there's a plot that I made which isn't pretty enough to show you, so that's why I didn't include it. But we do actually get an increase in moist static stability when we look at the all-model ensemble average. And if you average over the tropics, you get P-E reduced in some places by up to 2.5 millimeters per day. But globally, changes in P-E are pretty small. Now, one of the concerns of geoengineering that's often brought up is the summer monsoon, specifically over India and the Sahel. And the reason for that is we have seen this in volcanic eruptions. So the reason you get a monsoon circulation, there are two reasons. One, during the summer, the Tibetan Plateau heats up a lot. It creates a low pressure center over, and here's a relatively high pressure center, so you get air flowing from the Indian Ocean this way. So that's one reason. But in order for it to turn into monsoon precipitation, the air has to be moist. So it's also governed by evaporative flux from the Indian Ocean. And what we've seen after volcanic eruptions is if it reduces both of those, and you actually do get a reduction in the monsoon. So it's plausible we would see something similar for geoengineering. But don't really see much for this simulation here. So that's interesting. It's interesting for two reasons, or for a few reasons. And what I'd really like to do is compare this to one of the sulfate scenarios. So if the sulfate scenario also shows that there's no monsoon reduction, that implies there's some fundamental difference between the transient response of a volcanic eruption and the steady state response for geoengineering. If the sulfate aerosols do show a monsoon reduction, that implies there's something very different about sulfate aerosols and solar radiation, where one causes monsoon change and one doesn't. I haven't looked at that yet, but it's on the list. And one of the last pictures I want to show you is terrestrial net primary productivity. And this is a great one to look at because what it does is it integrates sunlight, temperature changes, CO2, moisture, all of that into one variable which basically says how much do plants like the new atmosphere. And as it turns out, they like it a lot. So there's a global increase in terrestrial NPP of almost 59 petagrams of carbon per year. And that's a 133% increase over the control. Now, if you look at the quadrupling of CO2 scenario, it looks very similar. The magnitude is slightly less, which says that, to me, that the dominant mechanism for this increase is CO2 fertilization. But under G1, you actually do get another 2 petagrams of carbon per year, about 2, and that's because you get all the benefits of the CO2 fertilization, but you don't have the increased temperature stress that you would have in a 4-times CO2 world. So, just to wrap up, experiment G1 shows an overcooling of the tropics by about 0.3 of a degree and an undercooling of the poles on average by 0.81 Kelvin. Changes in P-E are pretty small over the vast majority of the globe. This experiment shows no discernible effect on the summer monsoon precipitation over India and the Sahel, but that's not to say that's a robust feature of geoengineering. Other experiments might. Terrestrial NPP increases are mostly due to the CO2 fertilization effect, and we get a little bit more because of reduced heat stress. And this one goes to how effective is geoengineering at returning the climate to pre-industrial. So what I did is I took a root mean square using each grid point, and I said, okay, what's the root mean square for G1 minus pre-industrial, and what's the root mean square for quadrupling of CO2? And so basically, Smaller numbers here tell you how much you've returned the climate to pre-industrial. And temperature, you return it to within like 9% on a grid cell by grid cell basis. P minus E within 35%. And as always, there's much more work to be done. We have a special issue in JGR. Papers are being prepared for that right now. And hopefully I'll have more to tell you next year. So I'll put that up in case you want more information about GeoMIP, and thanks very much.
We have time for a question. Mike? Repeat the question.
It looked like there was a significant impact on the monsoon in Southeast Asia. Can you comment on that, and also on the plant productivity? Would that be affected by an increase in diffuse radiation from sulfates?
So the first question was the monsoon effect in Southeast Asia. It does look like there's something there. And in China. I looked at the monsoon areas that I thought of coming from a volcanoes background. Simona is actually working on a paper where she looks at all the monsoon regions. Some of them do show something. These in particular do not. So more analysis is needed. And the second one was regarding NPP increases from diffuse light increases. That is certainly possible. That's not the majority of the effect. Just because this graph looks so similar to the 4 times CO2, the dominant effect has to be CO2 fertilization. But I do agree, diffuse light, in as much as the models can do that sort of thing, probably does play a role.
Okay, thanks. So I think we have to go on to the next talk, is by Govindasamy Bala.
Okay, so what do I do?
You can go forward and back here with the mouse.
Okay, the title of my presentation has a little bit changed because even though we did this experiment with aerosols, we felt that this experiments were applicable to basically space-based geoengineering schemes as well. Okay, so mainly I think I have underlined their global hydrological cycle because I think still, if you want to really put some constraints and want to really have some kind of fundamental understanding, we could actually still get understanding only on the global hydrological cycle, which is basically here in this case, global mean precipitation. Okay, so let me just summarize what is the real thing that was done in this study. Basically, we fixed the total amount of aerosol, that is 12.6 megaton of total sulfate aerosol, and the idea was to vary this particular amount meridionally, in idealized fashion, to see how the global mean hydrological cycle actually responds. So we all know by this time that in a geoengineering scenario where you mitigate surface temperature change, you do have global mean, decrease in global mean rainfall. So now I think originally I wanted to actually see if I change the aerosol distribution, if I can mitigate both surface temperature as well as precipitation. That was the original idea. But as you will see, that never really panned out, and we were always getting, irrespective of where we put the aerosol, whether in the poles or whether in the tropics, you always get global mean reduction in rainfall. Okay, so these are the relevant studies prior to this particular work, where something has been really looked at by varying the either the solar constant or sulfate aerosols, putting in different places. For the first one is by Caldera and Wood. Here they varied the meridional distribution of the solar constant and looked at how whether Arctic geoengineering will work. And the next one is by Alan Roebuck and others, and they actually looked at the geoengineering by injecting sulfate aerosols in the tropics as well as in the polar regions. And there are a couple of more studies, Banvis et al., Banvis and Caldera. They basically wanted to basically here they varied the meridional distribution of aerosol to mitigate, basically optimize the climate. Their goal was again to optimize both the temperature change as well as precipitation change, but they found out that they can only optimize one at a time. And another important thing was, in this case, I found out that they have actually varied both the distribution as well as the total amount of aerosol in that case. So Our study is slightly different, that we wanted to see if we can, constrain by saying, total amount of aerosol is the same, but vary the meridional distribution. Then recently there is a paper by McMartin et al., and it got published in Nature Climate Change, and they looked at by varying both the latitudinal distribution as well as the seasonal distribution of sunlight to see, it's again an optimization paper. The main idea is, but I think in respect of all these studies, I at least had difficulty to find out if there is a clear, simple picture of global hydrological response to the latitudinal distribution of aerosol. That was the main idea of this work. So the model we used is NCAR model, and the 2-degree resolution, and we used the slab ocean as well as the fixed SST modes. The slab ocean model is used for climate change experiment, and fixed SST runs are used for estimating the radiative forcing. Okay, so here are the experiments. The first experiment is control simulation. So we use the current CO2 values, 390 ppm. And in the case of doubled CO2, it is 780 ppm. And then we performed 10 geoengineering simulations. In all those cases, we added basically the total amount of aerosol was 12.6 megaton. I'll come to the next slide where I show the distribution of the aerosol, how they vary. And the choice of 12.6 was basically, that was the uniform distribution that has a near zero global mean temperature change when you compare to the control simulation.
Per year?
No, this is a total amount of aerosol that is prescribed. So these are not injection simulation. Here, the aerosol concentration is prescribed in the atmosphere. There is no transport. There is no microphysics. Okay, so here is the distribution of aerosols that we have used. So you can see the horizontal line there. That is a uniform distribution. And then there are 3 tropical cases where the maximum is in the tropical region. And then there are 6 polar cases where the aerosol concentration is maximized in the polar regions. So we performed both slab ocean as well as fixed SST experiment, and this was all done by a student. So the experiments had shorter length scale. You can see that the fixed SST experiments were 30-year simulations, and the slab ocean simulations were all 60-year simulations. But anyway, by 25 years, the slab ocean anyway comes to equilibrium. So we used the last 30 years for the climate analysis. Okay, here is the, let's little bit look at the left side figure. It shows on the horizontal axis the radiative forcing, and the y-axis the temperature projection. But I think what I want to see is, there is a systematic variation. You can see that things are falling on a straight line. So on the top right corner, I have written not enough. So here basically the aerosol is not, and the amount of aerosol is not enough on a global mean basis to counteract the radiative forcing from a doubling of CO2. On the left, too much. So in all the tropical cases, we have too much aerosol, and in all the polar cases, not enough for aerosols. And look at also the precipitation. It also falls on a straight line. I think that is what I find this to be an interesting case. That is, it doesn't matter how you put your aerosol, the model always cares about the global mean radiative forcing. If the global mean radiative forcing is higher, you have a warming. If the global mean radiative forcing is lower, you have a cooling. And similarly, higher temperatures are associated with wetter planet, and cooler planet. Cooler planet is associated with drier conditions. Okay, so here is the bottom line analysis where we actually looked at what is the change in planetary albedo. So again, things are falling on a line. So this is in fact was a result that was found out by Caldera and Wood, where what they say is per unit change in radiative forcing, you have similar global mean temperature change. Okay, so here what I have plotted is delta T versus delta P. So you can again see things are on a linear line. So if you have more temperature, you have more precipitation. If you have if the planet is overcooled, then you have precipitation reduction. But I think what is very interesting is in all the tropical cases, we found the global mean precipitation actually as lower, and in all the polar cases, the global mean precipitation was higher than the uniform case. And another important thing is, as you can see here, the line really does not pass through delta P equal to 0 when delta T is 0. So, and in fact, you can see that it is shifted downwards in all the cases, whether it is land, ocean, or global, or the global mean. So, which basically again tells you it doesn't matter how you distribute your aerosol, the global mean precipitation is always lower. Okay, so here is our, here are some, this is GCM study, so we do have a spatial pattern of temperature change and precipitation change. So on the left, all are temperature changes, and on the right you have precipitation changes. Everything is relative to 1 times CO2. So in the first case, you can see that there is a warming, and as Ben Gravett showed, there is a spatial pattern of precipitation change. And the second one, what is shown is the case, which basically the uniform case, which mitigates the temperature, but it has a reduction in precipitation. And the third row, it shows a case. It's actually a polar case which has actually global mean mitigation of precipitation, but in that case there is a reduction. There is a warming. Overall, the planet warms. And the fourth panel, fourth row, it shows a case where you have temperature is mitigated, but precipitation is not. And then there are 2 extreme cases. For example, the extreme case with the polar, you have mean warming, and the extreme case with the tropical case, you have a kind of weakening of the hydrological cycle. Okay, so you can also look at as an optimization problem. You can look at the RMS error. So if you really go by the RMS error, you will go by polar 4. That is the minimum on RMS difference. And if you take the temperature as the key, then you will go with the tropical case 2. And if you really want to optimize both, you would probably choose the uniform case. Okay, following is I'm coming to the end of the talk. So these are, I think one thing is, these are idealized simulation. They are just designed basically to illustrate the basic fundamental properties of the climate system. And, there are many things that are missing in the model. The main thing is, this is not a full coupled model, and also aerosols are not, injected, and there is no transport, no microphysics. This is all prescribed aerosol. And anyway, these are the key messages here. I'll just put it up, and my time is up.
Okay. Thanks very much. We have time for a question. Yes.
In green cloud brightening, we find that the errors in the controlled precipitation, the observed precipitation, is approximately twice as big as the changes in precipitation when we do our green cloud brightening runs. Have you got any comparison with how the changes in the overall precipitation of the planet with the sulfate schemes compares with the errors or size of the changes in the errors between the control and the actual?
Please repeat the question.
Can you? Yeah,
No, do you understand?
No.
The question is, how do these results compare to marine cloud brightening cases?
Okay. I think what I can really say is for the global mean, as I had shown most of the linear plots, we had similar conclusion in the marine cloud case also. As long as it's really a function of the global mean temperature change or global mean precipitation change, they are really functions of the planetary albedo change. But regional things are totally different.
Okay, thanks very much. The next speaker is Kelly McCusker.
Hello, thank you for coming to my talk, and also thanks to the session conveners for a pretty interesting session. So this is some work that I've been doing with Kyle Armour, who's at MIT now, and my PhD advisors, Cecilia Bitz and David Battisti at the University of Washington. And I'm going to be talking about the climate response to abrupt cessation of solar radiation management. How do I use the mouse? Oh, okay. Which keyboard? This one? Okay. Okay, so there's been, at this point, a lot of studies on solar radiation management, and the bulk of them, I think, focus on kind of stabilized climates, or if they're looking at transient simulations, then they typically, we always focus on the global mean. So in these studies, so far, SRM is effective at reducing the changes that you might see with increased greenhouse gases. But I wanted to look more at what if something goes wrong. So technological failure or breakdown in international collaboration or an unintended consequence that was just too bad to deal with. And so people have looked at this already. We will get an abrupt termination, or sorry, an abrupt warming upon termination. So this is there a thing here? No.
There should be it's right there. Here.
Oh, sorry. Yeah, okay. So this is a paper by Matthews and Caldera in 2007 where they did like an intermediate model, and they show if you shut off an SRM, the temperature rapidly approaches what it would have, and they sort of showed a few different shut-off years and 2 different climate sensitivities. And there's been a few other ones that all of them have an abrupt warming. So these are some of the studies. These are not all of them. There's a couple more. And yes, including Alan Robach sitting next to me. In all cases, the temperature rapidly approaches what it would have. So what I wanted to explore is how what the spatial trends look like. So how far out of bounds are these spatial trends compared to trends that we may have experienced in the last century, say. And then also I wanted to explore what the effect of uncertainties due to climate sensitivity and due to human decisions, so what background emission scenarios there are. Okay, so here's how I did some of this work. So this is I'm using CCSM4, which is a fully coupled global climate model. And so this is a figure just showing global mean, annual mean surface air temperature for end of the last century, and then the business as usual, RCP 8.5. And then this blue here is this SRM scenario that I ran, and it basically ramps up a sulfate aerosol burden. So it's prescribed. It's similar to the way that I've done it previously in some earlier work. And so we geoengineer for 25 years. There's just attempting to stabilize over here this scenario. So what you get is in 2060, after 25 years, you get a really rapid, as expected, warming. So that I have 2 ensemble members, and I want to look at what happens spatially. And I should say that I'm focusing on temperature trends, and I've chosen to look at just summer in both hemispheres. And the reason I did that is because of the implications it has on global food production. Crop yields are very sensitive to temperatures. So here we go. So we have these are 5-year trends in summer in both hemispheres, and the axes are 8 and 8. So what we get is some of these regions are reaching 8 degrees Celsius per decade, and the global mean, the land mean is over 3 degrees Celsius per decade, which is already rather large. So now let's see what happens if you look at 20 years. Now remember, this is a pretty high background emission scenario, but it's definitely a plausible one. We have much more spatially uniform trends all over land. Basically everything is over 1 degree per decade. And the average is 1.3. So the question that I had then is, yes, we all know that those are very large, but how anomalous are these? So I want to put them in the context of the past century, and what I did is I just took a historical simulation and I computed 5 and 20-year trends throughout the simulation, starting from the year 1900, and I take the standard deviation of those trends, and I'm going to normalize in every grid cell by these maps here. So this is just the standard deviation of the historical trends, 5-year and 20-year, and they look kind of as you would expect. Standard deviations are greater for 5-year trends, smaller for 20. Standard deviations are greater in mid and high latitudes than the tropics.
What are the units?
This is degrees per decade, sorry. Yeah, units are degrees per decade. Okay, so here's what you get. So now the units are standard deviations. And basically, the colors that you can see probably from where you're sitting, they're all above 2 standard deviations from historical trends. So basically Africa, the Middle East, and South Asia, and Europe are getting greater than 2 standard deviation trends, and then the mean in general is over 1 standard deviation. 20-year trends are much greater. So now the axis is up to 6. So all these red areas are 6 standard deviations away from any from the 20th century 20-year trends. And the mean is almost 5 standard deviations. So what this means is you can see that they're spatially broad and they're very large and they're very anomalous. So as far as global food production goes, you know, some of these regions are already experiencing decreases in yield due to temperature changes in the last 30 or 40 years. And they're in some of the same regions that we have just seen large trends. And these trends are so spatially broad for the termination that there's no relief. So there's nowhere you can shift your food production to make up for any lost yields. Okay. So now I just wanted to quickly go through how sensitive these results might be to uncertainties. So in a GCM, we can't vary the climate sensitivity, but in fact, we don't know it, and it could be much higher or lower than CCSM4. So this is just showing a couple PDFs of what climate sensitivity has been estimated to be through various methods. And what you can see here in blue is that the IPCC AR4 models don't span the full range, so they kind of miss this high end. CCSM4 is somewhere in here. So how sensitive are these, are my results to this range of climate sensitivity, and then also to how does that compare to the timing of termination and what the background emission scenario is? So to do that, I just used a simple model, an upwelling diffusion energy balance model. This is just one example. I have a prescribed radiative forcing for the RCP 8.5, the same scenario as before. We have a stabilized climate for 30 years and a shutoff. And then here is the resulting temperature trend or temperature response. If we just postpone the shutoff to 80 years later, then as expected, we'll get a very larger rise, greater trend in temperature. So now this is for one background scenario and one climate sensitivity. So I'm going to show you a figure next that has a range of climate sensitivity. Okay, so now we're still looking at one background emissions, but now the axes are climate sensitivity versus 5-year trend. So I took the trend and right after shutoff, we've got the RCP 8.5. You can see this is no geoengineering here, and this is 20 years later shutoff. But what you can see is interesting is that the trends don't depend a whole lot on climate sensitivity, right? So they're fairly flat here. But if you postpone your shutoff to 50 years and then 80 years later, that's when you start seeing a jump in your trend magnitude. So it's actually more sensitive to the timing of the shutoff. Now, what about the background scenario? So here now I'm looking at RCP 2.6, so this is the lowest background emission scenario. Again, here's the trends. I'm just taking a trend from when the maximum radiative forcing change was. And we have a 20-year shutoff here. Again, fairly flat, not super dependent on climate sensitivity. Now, let's look, here's the shutoff after 80 years, and you can see there's not as big of a jump here. So basically, the point of this is that the background emission scenario is actually really important. So if you mitigate, that's the best way to avoid any sort of temperature trends like this. Okay, perfect. So in summary then, with high emissions, the temperature trends over land are well outside the bounds of the 20th century trends. And these trends are mainly controlled by background emissions or timing of termination. So I guess what I forgot to say earlier, but this is sort of one of the main points, is that low climate sensitivity still gives large trends, especially if you have a large background emission scenario. So low climate sensitivity doesn't save us. And then also because of the long lifetime of CO2, so these emissions don't just go away immediately, these potential dangers will exist indefinitely on human timescales. So this type of thing is forever. And so the only way to do SRM safely is that it must be accompanied by mitigation. There's no other way to do it. So thanks very much.
We have time for some questions.
Please repeat the question.
The question was, does the temperature always go back to business as usual, or does it ever actually overshoot and get worse? So I think in the global mean it wouldn't ever overshoot. I think regionally, probably not, but I don't know that, yeah.
Could you speak louder? I can't hear you.
When you terminate the SO2 submarine, surely what will happen then is the global warming rate will go up in accordance with the forcing, the current forcing, which is on the CO2 that's in the atmosphere.
Yeah, so he's saying when you shut off the SO2 or the SRM in general, the rate of change or the rate of temperature will surely just be dependent on the CO2 emission, the CO2 concentration. Yeah, that's exactly right. So it's the main control of your initial trends is what that change in radiative forcing is, and that is dependent on how much CO2 is in the atmosphere. So it's not as dependent on what the sensitivity is, the climate sensitivity. Yeah.
Sorry, we need to keep on schedule, so maybe you could talk to him afterwards. Thanks. And our next speaker is going to be Jan Egil Christensen from the University of Oslo, talking about climate engineering by manipulation of cloud properties.
Yeah, I'd like to start by thanking Ben and Alan for inviting me to give this talk, and I'd also like to thank my co-authors for contributing to this presentation. So over the next 10 minutes, I'll try to give you an overview of the mechanisms involved in the proposed geoengineering schemes involving clouds, and obviously I don't have time to give credit to all the work that has been done by also other people, but I will try to focus on the concepts, and so if you have questions, then please ask me, and I can maybe tell you some more about results. So first of all, there are basically two methods that have been proposed. One is has been around for a while, marine cloud brightening, which was suggested by John Latham more than 20 years ago. And the idea here is that we have these relatively thin low clouds over the subtropical oceans where they have a very strong cooling effect on climate because the underlying albedo is low, but their albedo is high, and the sun is high. And the idea is that if we can make them optically thicker by injecting more CCN, then we can enhance their cooling effect. And then we have this more recent idea of cirrus cloud thinning, which acts in the long wave, not the short wave. This was suggested by David Mitchell in this paper here in ERL. And these cirrus clouds tend to have a warming effect on climate. So the idea here is that if we can make them thinner, optically thinner, then by injection of ice nuclei, and I'll explain in a moment how that works, then that might also have a cooling effect. So just an overview first of marine cloud brightening. I mean, we know that the aerosol indirect effect, which this is based on, actually works. I mean, we see that from satellite pictures that show these ship tracks. Of course, this doesn't happen every day, but when the clouds are susceptible, we see these very strong signals over the oceans. And the question is, can we deliberately produce something similar to this? And this has been done in models, and I don't have time to show you a lot of results, but here's from one paper. There have been other papers like Parton et al. And Jones and Haywood also, that generally show that if you do marine cloud brightening on a large scale, you can actually cool down the global climate sufficiently to counteract the doubling of CO2. So that's what these models have been showing so far. But we know that these models have their weaknesses, and we don't really trust them. And I'll come back to that in a moment. So what we really need is also other approaches to this problem. And recently in a paper in Proceedings of the Royal Society, John Latham and co-authors suggested this field experiment where one would go over these subtropical oceans and really do dedicated experiments, starting with a single plume and then with multiple plumes and with aircraft flying at different levels to really try to nail down these processes and thereby validate the models. And we also know from LES simulations that what we're seeing in the climate models may not necessarily be correct, because this is running with a model that has horizontal grid spacing of 300 meters, which is 3 orders of magnitude finer than the climate models. And here we're seeing structures that we don't resolve in the climate models. So here, this is simulating ship tracks. And in this case, we have an open cell mesoscale structure, those are the cumulus clouds, and then we see a strong effect. Whereas when we have closed cells corresponding to a more polluted environment, we don't see any sensitivity. And it's not clear to what extent the climate models are able to reproduce these kinds of effects, and especially the transitions between these two regimes. So I'm going to show you now some results from work where we have been interested in studying the sensitivity to particle size and mass of injection of sea salt. And this is done in a climate model where we have inject 3 different sizes of aerosol. These are the modes that we have used. The 0.13 mode is the one that has been suggested by John Latham. And here's an outline of the model. So this is a state-of-the-art Earth system model with prognostic aerosols and prognostic cloud droplet activation, and also wind speed dependent sea salt. And here's a global average of some of the results. So we have increasing emissions on the x-axis here, and then we're looking now at percent supersaturation, globally averaged. And this is a busy plot, but the important thing to note here is that as we increase the amount of sea salt that we inject, we get a lowering of the supersaturation where the clouds form. And this is what we call the competition effect. And what this means is that it's getting increasingly harder to produce or to activate the aerosols as we have higher emissions. So that it means that the benefit of the emissions in producing cloud droplets is going to be much smaller than we expect. And it turns out that this is especially serious for the small particles, shown in blue here, that for these small particles we actually get a warming effect, and this warming effect is particularly large for the large injections. For the 0.13 micrometers, we do get a cooling effect, but also there we see tendency for saturation here. Although that's also depends on assumptions on vertical velocity. And if we turn off the competition effect by prescribing the supersaturation, then we get this dashed curve here. So we see that then we go from a warming to a cooling also for the small particles. So it shows that but this competition effect is real. So that experiment is just very idealized just to illustrate what's going on. And now I'm going to move to some experiments on cirrus cloud thinning. And in these experiments, I mean, the concept here is that ice crystals in cirrus usually form by homogeneous nucleation at high supersaturations. So if we can somehow force these clouds instead to form on a much smaller number of ice nuclei, we would get much fewer ice crystals, and these would grow very rapidly, and thereby they would fall out more easily as precipitation. And even if they were to remain in the atmosphere, they would also have a lower optical depth than in the unperturbed cloud. And so here is an illustration of how this would work. This is an unseeded cloud. We have a lot of small ice crystals. Here's the seeded cloud. The ice crystals are much larger. The cloud is depleted, and more long-wave radiation is allowed to escape to space. And there's some observational support for this, as shown here in this figure, that we see that around minus 40 degrees, there's a tendency for certain ice crystal properties to change, indicating that this may be a regime dominated by homogeneous freezing, and this a regime dominated by heterogeneous freezing. So the idea is then to go into this regime and force it to behave more like that regime by the injection. And I'm going to show you results from experiments running with CAM5. So that's also a state-of-the-art global climate model. And we're using a fairly sophisticated treatment of ice nucleation. And we have one control run, and then we have a seeding run where we have both homogeneous and heterogeneous freezing competing at low temperatures. And we assume that they activate at 10% supersaturation, whereas at homogeneous freezing you have supersaturations of 40 to 50%. And what happens is that these are meridionally average cross-sections. So we go from South Pole to North Pole, and you see that in the upper troposphere we have a decrease of ice crystal number and an increase of ice crystal size, which is exactly what we desire. And the resulting effect here is, again, a global average. So we see an effect both in the short wave and the long wave, but the long wave effect dominates. So the net effect is a cooling for, well, I picked out one value here, for about -2 watts per meter squared. So in summary, we see that GCM simulations, from GCM simulations, that marine cloud brightening may have the potential to cool climate. At least assuming that we are careful about the size and amounts of sea salt that we are injecting. And we've also seen that there is some potential for cirrus cloud thinning from these climate model simulations. But there are two items at the bottom here just to remind you that these GCMs have the limitations, so we have to be very careful at this point. And I think what these results are mainly telling us is that we need to do a lot more research, because this may work, but it may also be that the models are just oversimplifying. Thank you.
Questions? Yes?
Could you explain physics behind why when you increase the Aiken mode in brightening, you got a function? Because ship tracks, that's what they are, right? Massive increases in energy.
Please repeat the question.
Yeah, he's asking why is it that when we increase, what is the physics behind the result here, that when we increase the Aitken mode, which is the blue columns, when we do that, why we get this negative result? Well, what happens is that we get a very large increase in surface area, so that so we get a large increase in the competition for the available vapor. And what happens, as you see here, is that the horizontal dashed lines here indicate this one as the supersaturation required for Aitken mode sea salt. So you see that in the first case we are doing okay with respect to that. But as we go to higher injections, we get supersaturation lower than that's needed to activate the sea salt. So both the sea salt we're injecting and the background sea salt of that same mode will not be activated anymore.
Okay, thanks very much. We have to go on to the next one. Doug McMartin.
Thanks. So this is work, while this is coming up, with co-authors David Keith and Ben here and Ken Caldera. I'll let you read the quotes really quickly. Those are just there for you to entertain yourself while I'm introducing things here. Where's my... There we are. Okay, so effectively Ben already gave me the motivation for this. The issue that we're looking at here is that a lot of the geoengineering simulations that have been done either did something straightforward like uniformly turning down the sun, as in the G1 scenario of GeoMIP, or uniform aerosol layer, or something like that. There are some exceptions that Bala mentioned so he already provided the literature review for this. So if you uniformly turn down the sun, you don't exactly compensate for greenhouse warming. At some level, you do a remarkably good job, but not everywhere benefits to the same degree. And so that raises all these questions about regional inequality and the fact that some regions might suffer. So precipitation may be harmed in some of these monsoon regions and so forth. And then, of course, that leads to these questions.
if not everybody can agree on what the correct level of geoengineering is, who gets to set that global thermostat, or sort of whose hand is on the dial? So the question we asked is, can we do better by tailoring the distribution of solar reduction in both space and in time? So this is using idealized forcing. We simply turned the sun down. We did not do this with an aerosol layer. L0 here is a uniform across the globe, and then changing the latitudinal distribution either in a linear or a parabolic way, and then combining those with doing that in each season. So we have 4 different seasons, 3 different spatial patterns. That gives us 12 degrees of freedom. You can think of that instead of asking whose hand is on the dial, we're going to give you more dials and see how well you can do. You might already guess from Bala's talk that we might, this is not going to be a panacea. You're not going to improve things perfectly. So just a rough idea of what's going on here. This is just with 2 variables. This happens to be Northern Hemisphere September sea ice and tropical precipitation. Pre-industrial, you'll start somewhere. And then as you add CO2 to the atmosphere, that will shift your climate to some other point. And if you restrict yourself to having uniform reduction in sunlight, as you increase the amount of sunlight reduction, that will take you down some line that in general is different from how CO2 changed the climate. And you can pick where you want to be here, but you can't simultaneously compensate with 1 degree of freedom for both the precipitation and the Arctic sea ice. If you have more degrees of freedom, then those affect these variables differently. We simulated each of these patterns independently in HADCM3L. And so roughly speaking, with extra degrees of freedom, if you pick some linear combination of these, you can choose any climate within this region, and in particular, you could choose your climate to restore that. Of course, there's a lot more than 2 variables you care about. In this particular study, we looked at temperature and precipitation at each grid cell, normalized by the interannual standard deviation. So stack all of those into a vector B. So that's my climate due to 2 times CO2 is that vector. Sorry, I'm a controls guy. I have to have at least one equation. The matrix A here is estimating in the model what the response is to each pattern. So it's the same sort of thing as B. In this 2x2 state example, that's B is this vector, and each column of A is the vector to a different one of these points. And then U is just saying how much of each pattern do we have. If we assume linearity, that's not a perfect assumption, but it's actually not as bad as you might think. That allows us to predict what the residual climate would be for any linear combination of forcing. And then once you have a prediction of what the residual climate is, you can just go stuff it into some optimization. And of course, the only question there is, well, what is it you actually want to minimize or maximize? So let me just give you a couple of examples here. Here's one trade-off you can look at. So one obvious thing to look at is the root mean square deviation in temperature and precipitation over the entire globe. That's this axis. And you can think of this axis here as being my regional inequality. This is how bad is the worst place on the entire planet. So, for example, you might do a really good job in the globe as a whole, but somewhere on the planet gets screwed. If you only have 1 degree of freedom, there's only a limit to what you can do. In this particular model, as you increase the solar reduction, you make both of these metrics better. You get to some minimum in the global RMS, and in this model, if you keep increasing the solar reduction, you get a slight improvement in the worst case. If you allow yourself all of these degrees of freedom and optimize, if the only thing you care about is the global RMS, it turns out you actually can't improve that very much over uniform. That's actually completely consistent with what Bala showed. But if you use those degrees of freedom to try to minimize the worst case, or to trade off some combination of the worst case in the global, then you get some interesting results. In particular, you can get about a 30% reduction in the worst case without having much of a significant impact on the global performance. And it's not plotted here, but that also comes without increasing the average solar reductions. That's just redistributing when and where you do things. And then this is a common assumption that climate impacts are a quadratic function of climate changes. So a 30% improvement is sort of a factor of 2 in damages. So that's a fairly big deal in terms of reducing the regional effects, with a giant caveat, of course, that this is in a model. This isn't in the real world. So this is going to be a lot harder to do. Here's a second trade-off. So this is the same global RMS temperature and precipitation, and now looking at northern hemisphere September sea ice extent. And now I've added in a constraint on how much average reduction you can do. So here's our pre-industrial baseline. By definition, that's our 0 point in terms of temperature and precipitation anomalies. You can see immediately this model doesn't get the sea ice reduction as strongly as it should. But the general idea here, as you increase a uniform solar reduction, there's basically only one variable you can change. You're stuck moving yourself along this line. With multiple degrees of freedom, you have a choice about what you want to minimize. So for example, if you only care about the Arctic sea ice, you will push yourself in this direction as much as possible. You follow this line as you increase how much you're allowed to use. If you only cared about the global RMS, you actually follow this line. And if you weight some combination, you can fall somewhere in between here. And just in particular, I wouldn't trust the quantitative results out of this particularly, but at least the qualitative idea, and this again is consistent with some of with things that Alan has done and things that in Caldera and Wood, saying that you can get a recovery in the Arctic sea ice with less of a solar reduction burden. So that's an idea of what you can do. There's a couple other trade-offs indicated in the actual paper you can go look up. The bottom line here that I'd like to say is this idea that we're going to go set the global thermostat is a little bit of an oversimplistic metaphor, and that at least in terms of, if we're ever going to implement some form of SRM, we should do it as well as we can. Of course, there's a couple of caveats here. First of all, as I said, this is in a model. Second, if you were to try to do SRM with stratospheric aerosols, you can get some latitudinal distribution. You might not be able to alter the seasonal distribution as rapidly as we included in here. If you do this with marine cloud brightening, you could certainly alter the temporal distribution much faster, and you could get some longitudinal degrees of freedom as well. And then I actually forgot to ask Gavin. Somebody told me this quote, and I thought it was perfect. So I think this is attributed to Gavin. What happens in Vegas doesn't stay in Vegas. You don't get to just pick and choose. This region gets its climate, and this region gets its climate. We all get to do our own thing. So you do still, of course, have this issue about who decides what the climate should be. And then I will end there with this other question here, which is, what is the right metric to consider in all of these? I'm not the first person to do temperature and precipitation normalized by the interannual standard deviation, but that's obviously not the right thing that we actually care about. So I'll stop there. Questions?
Alan. Short question.
So the question basically is whether marine cloud brightening, since marine cloud brightening by default has a different latitudinal effect than uniform uniform stratospheric aerosols, did I look at that comparison? Let me give you a two-part answer. The first is the stratospheric aerosols overcool the tropics if you use a uniform distribution, but nobody ever said you have to use a uniform distribution. So you could get something better by tailoring that distribution. And the second answer, I think, is if you really want to go down this avenue, the right answer might be to combine some degree of stratospheric aerosols with some degree of marine cloud brightening. And that gives you both your temporal and your spatial degrees of freedom to try to mix and match and sort of do as well as we can.
Thanks very much. The last talk of this geoengineering part of the afternoon is by Simone Tilms.
Okay, I would thank you first, Ellen and Ben, for inviting me for this talk, and I want to acknowledge my co-authors as well. And where does it? Okay. So I'm talking about the stratospheric aerosol seeding approach here, and as we know, aerosols cool the climate. We heard a lot about this. I'm not talking about climate impacts. I want to focus on the chemistry in this talk, and especially on changes in ozone. And what I want to look at is the very short-lived halogen species, because usually we look at the evolution of chlorine, and we know that chlorine is decreasing in the future, which will lead to less ozone depletion in the future. But we often ignore in most models the very short-lived halogens, and this is what I want to focus on in this talk. In addition, I want to talk about the impact on UV on radiation. So as an introduction here on motivation, I want to look at past observation. And this is actually a study that was done by Solovich et al. Looking at anomalies from column ozone in percent from 1980. And this is a busy plot, but if you look at the black line, these are the observations. And you do see the general trend of ozone going down with time. And this is due to the increase of halogens that maximized by the end of the 90s in the stratosphere. But also you see these dips in ozone. And this clearly indicates that if we have more aerosols, we do have more ozone depletion, and this is in mid-latitudes. We know that in high latitudes we get more ozone loss as well. And this model studies also show that if you run the model without very short-lived halogen species, especially bromine, you wouldn't catch these dips very well, but you would define where there wasn't any aerosols or no enhanced aerosol regions. So really, halogens or the short-lived seem to matter in the past, and our question is, how does that matter in the future when we are already in a much more declined time where halogens are much smaller than they were in the past? So what we do, we use the whole atmospheric model, WACCM, which covers the entire troposphere, stratosphere up to the mesosphere. We have full stratospheric chemistry, heterogeneous reactions, and how to describe geoengineering. Here we have two aerosol surface area density size distributions, or aerosol distributions described by surface area density. And the model will then calculate the aerosol distribution from this information. The one is the baseline, and one that is the geoengineering distribution that we have taken from a previous model study from Russia et al., where sulfur was injected in the tropics and distributed over the globe. And so we do contrast these two in the following. And also, we look at some, in the past we have done a model study where we use a fixed surface area density to cool the climate. So here we have a baseline temperature change in an A1B scenario from 2020 to 2050. And then we have a decrease in the geoengineering case. We see that temperature really go down about 0.9 degrees. Here. And what we want to focus in this study, we want to focus on chemistry. So we take fixed meteorology and run the model over and over again. So we're not looking at dynamic changes, just at the chemistry here. And so, as I said before, we usually consider in models the long-lived halogen species. These are the ones that come from the CFCs, HGFCs, halogens. They increase drastically and then decrease. And we have the chlorine and the bromine components. And chlorine is usually much more abundant than the bromine abundance. But for the very short-lived species that are not included in this plot, there is a wide range of what is possible. And those come from biological sources in the ocean, so they are constantly there. They're not changing like the anthropogenic ones. And they can range between 1 or 10 ppd from observation. So when we compare to recent satellite observations, it's very likely that we are in the upper range here. And so there are also chlorine very short-lived species, which are, have a lower contribution in general. So what we are doing, our case is set up in a way that we run 3 scenarios. One is a very short-lived species with no very short-lived species, one with 6 ppt bromine and one with 10 ppt bromine and 100 ppt chlorine. And so I want to jump to the results right away. And what you see here is a change in column ozone based on the 3 cases that I just described. And I'm just looking at column ozone here at a specific time in spring, because this is not the ozone hole season. We know that during the ozone hole season, the impact is largest. But even here in summer and in mid and high latitudes, there's a considerable impact if we consider very short-lived species. So in the 0 case, there's actually an increase of ozone. And this is, for the chemists here, that we have a decrease in the NOx to NOx ratio in this region. And so depending on how much halogens we have in the stratosphere, this cycle or the ozone increase is larger than the ozone decrease from halogen components. But if we add more bromine here, we see that this actually changes the sign and we go to a negative impact. But especially in the mid-latitudes, in the northern hemisphere, we see a drastic increase. It is a doubling of what we had before. It's only, I mean, if you think it's a small impact, but it goes from 0.1 degree to up to 5 degrees. Here, a decrease in ozone, in column ozone. And even also the high latitudes in summer have a significant impact. So and then this is really important when we think about the impact, and that's always the question, why do we look at ozone changes? Is the impact on UV, especially thermal UV, which is weighted to the sun burning spectrum. And so we do use a comprehensive radiative transform model, the TUV, and we look at the changes in the surface UV, especially from the B spectrum here because of the changes in ozone, which you can see here on the right. So what you see is a difference again between geoengineering and the baseline simulation of UV erythemal for my 3 different cases and the ranges of very short-lived species. And the blue here is a negative, so we do get a decrease here for the 0 case for the erythemal UV, and this is an annual average, but the high latitudes are even considerable in this not considered in very short-lived species. But going to the highest level, we do see a drastic increase. Actually, I wanted to show the names, but you can read this here. So we do get a strong increase here, even in mid latitudes, 4 to 6%, and this will have a large impact. So really, depending on what we assume for very short-lived species, the impact can be very different. And so also important here is when we look at UV changes, we should look at the scatter of aerosols, because not only ozone changes the UV, but also we have aerosols that will scatter the UV. And we did study this, and what you see here is erythemal UV, once for the 0 case and once for the high, very short-lived case. And the effect from the aerosols is shown here at the dotted line. So you see a decrease in UV actually. But then the ozone is showing this dashed line, and the total is in solids. So actually we do really see a strong difference again, depending on what abundance we choose for the very short-lived. And with the largest abundance, we come close to actually the changes in the 80s and the 90s. And with that, I want to conclude that it is really important to have a better knowledge of the composition of the atmosphere, because even things that we haven't considered can have a strong impact, and to really quantify what the impacts are on just this example can be really drastically different. So therefore, there are still large uncertainties and things that we don't understand in the atmosphere, and before geoengineering should be considered, there is much more research to be done. And with that, I want to finalize. Yeah, thank you.
Questions? Yes, Phil.
Yes, Simona, can you tell me on your charts it looks like at around 50 degrees that the UV reaching the surface is increased. Is that right? Is that sort of critical?
Repeat the question.
Yes, certainly.
Repeat the question.
What? Oh, if at 50 degrees, is it a critical level if UV increases? Well, if we stay at 50 degrees, we certainly see a change, especially if you go one plot before this, between increase and decrease, depending on what kind of scenario you choose. So it is really critical. It really depends on what is the amount of very short-lived you choose. But you're right. This is the latitude where it skips, or where the sign flips, basically. Thanks.
Thanks so much. Or do you want me to do this?
Okay.
So the next three presentations are on carbon sequestration monitoring, and the first speaker is Tom Daly on subsurface monitoring of CO2 sequestration, a review and look forwards. This is an invite talk.
I could probably use the mouse. So I'd like to thank conveners for inviting me to speak on subsurface monitoring. As it says, I'm going to give a review and a little bit of a look forward at subsurface monitoring. We have here a picture of CO2 emissions from a pre-O'Brien pilot test that was venting to the atmosphere, and that's about the clearest look we'll get of CO2 in this presentation. What I'm going to do is give a review going back really to the 1950s of storing CO2 underground, or at least injecting CO2 underground, not necessarily with the hope of storing it, look at some monitoring examples, and then talk about looking forward for large-scale sequestration and some ideas that I have. So going back, I did a little bit of a literature review, and the earliest records I could find of subsurface injection of CO2 really starts around the 1950s of oil companies looking to enhance recovery. You see a paper from 1951 they called carbonic acid injection. And an interesting early monitoring study in 1959 there, Booty and Geophysical Prospecting, who was looking for mineral water and was using some atmospheric sampling to try and find that. I guess Perrier had value back then too. Going to the 1970s, we start to see our first large-scale CO2 EOR tests. The SACROC site, which some of you may have heard of, began work where they were talking about 37 megaton injection over 9 years. Interesting reference to 1978 SPE Journal FAR talked about the first time seismic as a reservoir analysis technique, and he had an interesting comment there. Until recently, pore fluid identification was considered beyond the resolving power of the seismic reflection method. And fortunately, we've, as I'll show, I hope, progressed beyond that. We see the first use of induction logs for monitoring a CO2 pilot flood in Richardson. And there's also, this is the beginning of early climate change concerns in this National Academy report. I have a picture of the cover there in 1977, which talked about the problems with CO2 while people were injecting CO2 underground, and I don't think the links were really being made at the time. Moving into the 1980s, we start to see really the beginnings of subsurface monitoring for reservoirs. Goodrich talked about 19 projects ongoing, but the abstract really has no mention of monitoring. SFOR and Globe talked about quantitative monitoring using pulse neutron logging for CO2 saturation. This is moving into 1982 now. We see the first use there in 1987, or the first reference I could find of really looking at using specific dedicated monitoring observation wells, which is something I'm going to be talking about later. And then an important paper, I think Wang and Nur starts looking at the effects of CO2 flooding on wave velocities, really starting to look at the rock physics that's involved. Moving into the 1990s, we have mature monitoring tools. Wang and al. talk about the McElroy CO2 flood, which I'll show a slide on in a minute. Wang and al. talk about integrating reservoir models and seismic monitoring, what is now sort of the accepted method of doing things. Lumley in 2001 stated there's now 100 total monitoring projects using 4D seismic, so you can really see the change now to active use of seismic monitoring of reservoir projects. So now coming up through the 90s into the early 2000s, actually into the present, we have the first large industrial sequestration field tests, Sleipner project using 4D marine seismic, Weyburn-Midale, which is also an EOR project using surface seismic monitoring, the Insala project, which demonstrated the successful use of INSAR, looking at ground surface deformation as a monitoring tool, the Snovit project is again using marine seismic. We had a number of research pilots coming online, the FRIO project with cross-well imaging and continuous fluid sampling, Nagaoka project in Japan, similar methodologies, intensive well logging, the Otway project in Australia where we had multi-level continuous fluid sampling in the subsurface, CO2 sink project in Germany showed the success of ERT, which is electrical resistivity tomography. It's looking at the electrical properties of rocks for monitoring CO2. And the US DOE partnerships started to ramp up in this time period. Particularly now we have Cranfield and Decatur ongoing, and we'll be hearing about Cranfield. So this is a slide many of you may have seen before, looking at the Sleipner monitoring done with 4D marine seismic. It's really a classic case, a really beautiful example of the success of seismic monitoring. You can see here, and these are maps that in the lower left of the horizontal slice through the plume of the change in seismic reflection amplitude growing over time. And on the right-hand side, a vertical slice through the plume, again showing the reflectivity amplitude changing over time. And this data set is really one that caused many people to come to believe that seismic monitoring, in fact, worked really well and was the answer, and this is what we needed to do. And I'd like to put a little bit of a caveat on that and say that we do need to have some other information besides seismic. And so this has been, I think, shown kind of well by David Lumley on the left here in a paper he did in 2010, where he looked at a numerical model based on the Sleipner site of one injection of CO2 in one layer. Sleipner, they think there's 7, 8, 9 layers that have taken CO2. You can see the Sleipner data on the right and the model data on the left. And the problem is that gas in seismic data can cause artifacts underneath the gas layer, which can look a lot like other gas layers. And the reason, or the way that the industry and that the Sleipner folks come to convince themselves of what's happening is to combine the reservoir model with the seismic data. And that's what you see in the picture on the right. The purple section is a reservoir model where they've gone through the flow in the subsurface and matched it to the matched it to the seismic data. And this is how you build confidence that your seismic data is correct, but you still have to be really careful of these kinds of anomalies like is demonstrated on the left. So the Sleipner case, there was no monitoring well, so they still don't really know exactly what's going on in the subsurface. Once you have monitoring wells, you can do a much better job of imaging the CO2, and this is an early, very good example from the McElroy pilot test. This is seismic crosswell imaging. You see two different resolution levels. The one in the center, this is the seismic velocity anomaly caused by the CO2. The one on the far left has much higher resolution. The wells are closer together, and you can start to see the stratification in a better way. A Lost Hills pilot project that I was involved with around the year 2000 brought into play the idea of multi-physics. So we now have not just seismic imaging, but electrical. So we had and we also had two components of seismic imaging, the shear wave velocity VS, the P wave velocity VP, and the electrical conductivity sigma, all of which were imaged with crosswell tools in a fairly small scale pilot. To give you the figure on the lower right is showing the saturation of CO2 in oil. Again, this was an EOR oil flood where there was methane, oil, and CO2 in the subsurface, which requires really multiple physics measurements to understand their relative saturations and the effective pressure, among other things. On the lower left, we see an interesting study I was involved in where we did single well imaging from one well. The bright reflector you see, we believe, is CO2 gas accumulating in a hydrofrac zone that was pre-existing from a water flood. So moving up now really to the present, the Cranfield site, and I'm going through this really quick. I'm not going to give you background on these sites. Some of you may be aware of them, and you can certainly look up references. But at Cranfield, we had many scales of measurements. We had surface seismic, which is shown in the top right. The red and blue is just parts of the wavelet, the surface seismic wavelet. We had a much smaller scale measurement of crosswell seismic on the order of just a few tens of meters, where we're actually able to, we think, get a pretty good picture of the CO2 distribution between a couple of wells. We are interpreting the seismic data for CO2 saturation using some rock physics relationships shown on the right. We're using what's called a patchy saturation methodology, in which the relationship between velocity and saturation depends on the patch size of CO2 mixed in with brine. In this case, we're in just a brine reservoir with CO2. You can see there's those lines. Which of those lines we're on, we don't really know. And so we need other methodologies to try and understand that. And it also impacts the frequency of measurement we're making, which is the other curve shown here. So to try and get at this patch size, we're driven even smaller scale measurements, which is core scale measurements. So we did this here for Cranfield, and you're looking at a CAT scan image of a core, a piece of rock that's had CO2 injected in it, and the bright spots you can see are where the CO2 is accumulated. So we measure the velocity in this rock, we can get the saturation from this CAT scan image, and we can get the relationship between velocity and saturation, and from that we can even estimate the patch size, which to some extent we can see from the CAT scan imaging. So that's the Cranfield test. I'm going through this really quickly for time limitations, so feel free to ask me later if you have questions about any of these individual sites. But I'd just like to say that for review, the monitoring development from the oil field operations has given geologic sequestration the basic tools needed to provide assurance for development of carbon capture and storage. But I would say with a caveat that we still need to be more quantitative in our understanding of saturation. And now I'd like to look forward a little bit and think about the difficulties we're going to have when we start going to really large-scale operations with multiple injection wells over tens and hundreds of kilometers possibly. We have regulatory requirements now in place from the US EPA for monitoring wells, and I think this is going to drive us to a need for more standardized, less expensive monitoring using adaptive borehole monitoring and modular borehole monitoring, which I'm going to describe now. So the need for adaptive borehole monitoring, I think, is because the plume growth will be uncertain in the initial injection period, and remote monitoring is unlikely to satisfy the regulators at many sites, like the Sleipner example of how many layers of the CO2, where exactly is it, and we now have EPA regs that require a monitoring well. So I think direct measurement via borehole monitoring will be, in many cases, required, and an example of this is having fluid sampling and borehole scale geophysics at certain locations where you have monitoring wells. The number and location of monitoring wells will be best determined in some sort of iterative adaptive method as the project progresses. An example of this is some work that was done a couple of years ago by Burkholzer and Zhao. These little yellow spots in the blue background are actually 20 different CO2 injectors in the Illinois basin in central United States. And what a real large-scale project would look like, or large-scale sequestration would look like, is many projects which begin to interact. And the colors here are pressure. So you start to get built up in the pressure field in this large regional reservoir over 200 kilometers. And one individual plume looks like the plot in the lower right. And my idea is that what we'll need to do is start to have an organized set of monitoring wells. This is much too large of an area to be doing surface seismic on, like we saw at Sleipner and in other cases. So we're going to have to be doing some point measurements, probably trying to straddle either side of individual injectors, so obviously be cost limited, and we'll have to try and be rational about how we do it on a basin scale. And how exactly this will play out remains to be seen. What is in these wells is what I call modular borehole monitoring. And my colleagues Freifeld, we first looked at this in the Otway pilot in Australia, where we had a single monitoring well. We put into it geophones, pressure and temperature monitoring, and multiple levels of fluid sampling. And I won't go into much more description of this except to say when we actually did it, the problem we had is we were trying to put a whole bunch of measurement cables into a little well, and there's actual real deployment problems here of getting it all in place. And we realized we need a better way to do this. So we've now looked forward to what we call modular borehole monitoring, where you can get all these tubes into a flat pack. You can be more intelligent about it, like putting tubes in tubes, where you're doing fluid sampling. Instead of having two separate ones, you now have a single one. You can have a bundle of fiber optics. We're getting much improvement now in fiber optic technology in terms of sensors. We're deploying some geophones in this particular package, which are stainless steel welded to give them better survivability. So now we employ this with just this one yellow flat pack and another spool for geophones. You see a geophone there. We can have these in a semi-permanent deployment and get seismic data that looks like this, pretty good quality, over about 1,000 feet in the well. And this is right now pretty much the state of the art to get a permanent string of geophones deployed in the well. But to look forward, a field test we did here at this Citronelle site is to look at fiber optic cable itself as a sensor. So there's new technology now where every meter of the fiber cable can be used as a seismic sensor. So in this 3-kilometer well, we actually can get 3,000 sensors instead of the 18 geophones that we did in a traditional way. And I think this is actually a look at the future because it'll be cheaper, we'll have more sensors. It's not quite there yet, and we're just right now analyzing this data to see how comparable they are. The sensitivity isn't there, but the technology will improve, I believe, and we should be able to get more data out of less space in the well in a less expensive way. So that's my little bit of look forward. A quick summary, I think multi-physics is important, multi-scale measurements is important, and multi-purpose wells will be important. And with that, I'll take questions if there's some time.
Any questions?
Right. Yeah, so the question is, should we really be trying to characterize every molecule of CO2 in the storage reservoir, or should we be interested in looking at what may be leaking out, which is what we're really concerned with? And I would say that the latter, that we should probably be doing some focused studies on trying to find a smaller amount that's leaking out. And that's one reason why having the whole well instrumented becomes important, because you really want to start looking above just your storage reservoir. You're going to need some monitoring of the storage reservoir so that you know that your injection is progressing as your models are predicting it will. But what you're really interested in is what's getting out, and that'll require monitoring above the reservoir, and including probably fluid sampling, pressure monitoring, seismic, and some other sort of physical method to remotely detect it.
Thank you. So the next speaker is Julie Dickoff on time-lapse seismic signal analysis for Cranfield EOR CCS sites.
Good afternoon, everybody. I'd like to thank you for attending my talk. I'm going to talk a little bit more about what Tom just discussed a little bit, time-lapse seismic signal analysis for Cranfield, Mississippi, which is an enhanced oil recovery field and a CCS site. It didn't work. The motivation for this study comes from needing to understand the sensitivity of fluids and seismic data, both for production of hydrocarbons, but also for CO2 storage. I'm first going to give you a little geologic background and production background of the field itself. Then I'll discuss the seismic surveys and well log information we have available and go through the workflow that we used for this analysis. I'll then conclude with some initial findings that we have, as well as some future work that we will be doing. Cranfield, Mississippi is located right here in southwest Mississippi in the southeastern United States. The entire field itself is 383 square kilometers, but the 4D area that I'm looking at is just 29 square kilometers. It's a shallowly dipping anticline with about a 2-degree dip and has a large gas cap present in the middle. The reservoir itself is a clastic reservoir located at about 3 kilometers in the Tuscaloosa Formation. It's comprised mostly of lithic fragment-rich sandstones, muddy sandstones, and cross-bedded conglomerate cherts. The field was originally drilled and produced by Chevron from 1943 to 1966. The oil and gas were both originally produced, but the gas was re-injected for pressure maintenance. In 1966, the gas cap was produced, and it left residual oil and gas present in the field. It's currently under a CO2 flood by Denbury Onshore out of Plano, Texas, and they use supercritical CO2 from Jackson Dome, which is a natural CO2 source located here in Mississippi. The field itself is located right down here. We have 2 seismic surveys. The first one was shot in 2007 pre-injection and was shot over the entire field. You'll see an image of it in just a second. And then there was a monitoring survey shot in 2010 after 2.5 million tons of CO2 had been injected. There's a detailed area of study set up which has 1 injection well and 2 monitoring wells. One of the monitoring wells has repeat sonic data as well as mineralogy data for the site. And the 28-1 injection well is located in the middle of the volume, which has an oil saturation log, as well as mineralogy data. This is 2 images. This is a baseline seismic survey 2007. This is the location of the entire field. The pinks and purples that you see represent residual oil and gas, whereas the blue represents higher water content. This is the 4D seismic area that you see. This is just the 29 square kilometers in the northeastern part of the field. What you notice, this is a qualitative image of the field itself. They are on the same color bar. So when you take a negative residual oil and gas from the 2010 survey we have, subtract another negative, you're going to get a less negative image here. And the X's represent a qualitative amount of how much CO2 is injected at each well. So for example, you see a large X here and a coherent response located in this area, which corresponds to this area of higher water content you see right through here. On the other side, if you look past the fault, you also see a large X here representing a large amount of injected CO2, and you see a significant amount of residual oil and gas, but you don't see this same coherent response here. We hypothesized that the residual oil and gas in the field was masking the effect of the CO2 once it reached a certain saturation. These are the two cross-sections of the seismic survey. This is the baseline survey located at the reservoir. This is a P-wave log from the 28-1 well located within the volume. And this is the repeat survey, and again, here's the reservoir and the P-wave log coming down. When we originally differenced the two data sets, you could see a similar pattern anomaly to what you see in what was done initially. And this is the location of the 28-1 well, and this is the location of the DOS area, the detailed area of study, which are the two locations that were used for analysis in this case. The blue represents, in this case, the residual oil and gas, just set to a different color bar to stay standard for this entire presentation. I originally did some fluid substitution work with a Gassman-Wood workflow, and it was used to predict and quantify a change for different amounts of CO2 saturation. I used two different wells for this. I used both the 31F2 well, which had the repeat sonic data, and I used the 28-1 well located within the volume for a model-based inversion. The 28-1 well has residual oil log, and we used a 30% residual oil saturation to stay constant. These are the 31F2 P-wave logs that you see. So I know it's difficult to see from where you're sitting, but if you look through here, it's from 3 to 20% CO2 saturation that we predicted different curves for and compared those to the repeat log that we have available. Any point for the computed saturations that matched the original repeat log, I then plotted up, and we found 19 points where everything coincided. So from this, I created a saturation curve just to predict what saturation we might be looking at, and it looks to be about 9% 9% CO2 saturation on average throughout the field. At the 28-1 well, I did the same thing, but for a different purpose. So again, from 3 to 20% CO2 saturation, and this is the difference between the computed saturations and the original log, because there is no repeat sonic available at this log. I used this well for a model-based inversion coming up in just a bit. We first cross-equalized the data set using a trace-by-trace comparison and was only shifted in time, so there was no phase shift in this case. The 2010 survey was used as a reference to shift the 2007 survey, and it turned out that only a small time shift was actually needed. This is the cross-equalized difference. This is a map view of the field, location of the 28-1 well, and this is a cross line located here. This is the 28-1 well P-wave curve coming down. And you can see this coherent response come out in the difference through the reservoir right here. What you notice that you also see some other effects below because of a velocity pushdown due to the gas in the field. From there, I created a model-based inversion which transforms seismic reflection data into an acoustic impedance volume based on the rock properties we had available at the well. I extracted a wavelet from the original 2007 data set and then did a well tie of the P-wave log from the 28-1 well to, using the wavelet to the seismic data. I then built a strata model based on the changes in lithology and ran the inversions for both the 2007 and 2000 data. This is the result from the 2007 data, and this is the result from the 2010. What you notice once we difference the data, this is a comparison of the inversion difference and the cross-equalization difference. You can see this fault being imaged extremely well, which should actually not be the case in an inversion because your rock properties, unless you have fluids migrating through them, should not change in a constant feature. And we are fairly confident that our fluids are not migrating through the fault. But what's important to notice is you see the same pattern anomaly coming through in both of these areas. So there is a significant amount of work to do, but when you look at the quantities of these two, they're fairly different. This is the cross-section of the model basin version, which you can, again, see a coherent response through this reservoir, but you can also see these responses coming out below. Because of that, we computed the time delay below the reservoir in order to quantify the velocity pushdown effect. This is a cross-section of the time delay that we used at about 2,850 milliseconds, again in this cross line through the 28-1 well. What we found is that the average change is about 1.2 to 3 milliseconds, which translates to an average change in velocity of 250 to almost 600 meters per second, which is fairly significant. So because of this, we looked at the quantities of everything we computed. And what's interesting to note is that the maximum change from the acoustic impedance at the 28-1 well is actually similar to the average change computed from the aversion. On the other hand, the time delay suggests it should be about 2.5 times larger than what we see, which corresponds to the maximum change from the inversion. So somewhere in here, we're on the right track, but there's a significant amount more work to do. And then again, our average saturation curve suggested an average CO2 saturation of about 9%. So from here, I now have second well location to integrate into our data set in order to constrain the inversion a bit more. However, we still could use some more well data. We'll be doing fluid substitution at this well as integrating it into the aversion, and we're going to look at some pre-stack AVO analysis and hopefully work on the seismic footprint that's present. So with that, I'd like to thank several people. Curtin University was a big part of this project. This project stems from several different national labs as well, and my advisor at University of Texas as well. So with that, happy to take questions.
Any questions? If not, let's thank the speaker again. Thank you. So the last speaker is Alan Mew on rock physical properties. This is an invite talk also.
Hi, thanks for sticking around. So I work with NETL in Pittsburgh and with the University of Pittsburgh, and going to talk about a number of different aspects that we've been looking at in trying to identify CO2 in a reservoir and considering long-term seismic monitoring. So we've seen a couple approaches already, and I thank Tom for giving some background to the whole sequestration and seismic scene. So we have multiple 3D seismic surveys at a Permian basin in West Texas, and I'm using SEM, micro CT, image processing, as well as laboratory velocity measurements to predict changes in the reservoir properties with long-term exposure to CO2. So it's a vuggy carbonate reservoir. Just to keep in mind, we have a reactive reservoir. So to blast with math like I'm not supposed to, I have the ugly Zoprowitz equations here, but what we're going to be looking at is AVO, so we're looking at multiple angles at a common midpoint and comparing the traces and noting that with a different fluid inside of a matrix, we will have different VP, VS, density, and attenuation factors affecting the outgoing waves that are recorded in a 3D survey. So in our rock, what we expect to see, brine versus CO2, is a type 3 AVO anomaly at zero offset, slightly negative, which is the solid line. This is the number of other returning waves from the Zoprowitz Explorer. So we have pre-stack data here, and instead of using the ugly Zoprowitz equation, we fit a curve to a given point on the stack and use fitting parameters. These coefficients are physically defined. They represent various properties of the reservoir, but when we just use them as fitting coefficients, we can map based on these particular coefficients. So we use 1/2 A plus B, which, and then overlay it with the reflection survey. And this survey was taken after an injection, and we sort of have some anomalies here. Here's the well, and it's sort of a double-layered reservoir here, so we can see some yellow and red. So that's the anomaly that we initially decided that we would call CO2. Some standard Gassman fluid substitution doesn't look great here, but it's mappable. But I'm more interested in the changing reservoir with time. So in the lab, we are measuring hydrostatic. Well, we're compressing the rock hydrostatically, and we can flow CO2 and various fluids through the core samples. And there's a transducer on receiver on the core ends to measure the velocity of sound in the rock. And so my take on porosity is that we have to understand what parts of the pores are changing whenever they're compressed. So maybe an introduction to compliant porosity. This is the closable porosity around the stiff pores that I'm trying to map in CT scans and SEM scans. We find velocity dramatically increasing at the low effective pressure range, which is the closure of the compliant pores. So the quick, here's the ugly right here, but the quick nice one is that this negative exponential, this subtraction of a negative exponential is the early effective pressure pore closure, and then the green line is the limestone itself reacting to increased pressure. But in our rock model from Shapiro, we quantify compliant and stiff porosity. So the model fits what we've observed. This is air as the pore filling fluid. Can I go back one? Oops, sorry. This was CO2, and you can see this is the phase transition too, and we're filling it with CO2 in this model at that CO2's density and bulk modulus at that particular pressure. But so it's fitting our model. Our model's fitting our observed data, so we're pretty happy about that. And so as a setup to exposing the rock to CO2 and acidifying the waters and potentially dissolving the calcite and dolomite in the limestone, we took before UCT scans. And so this is our highest resolution, so it's about 1.5 microns per pixel, and it's hard to tell whether we can even map the closable porosity in this. We have our large pores, but so are these the compliant pores that are being closed with increased effective pressure? So some of my rules to looking for compliant porosity is close distance to the pore walls. So this is a local thickness map, which basically draws a line from a particular pixel to the edge of the pore wall and colorizes it by that distance. So the yellow is what I would call stiff porosity, and the more cooler colors are the closable compliant pores. Another idea is that elongated pores are more easily closed. So we also mapped in SEM over large data sets, 3 perpendicular plane, 40 by 80 centimeter SEM montages, pore size and aspect ratio, and pore orientation. So we got 3 large perpendicular planes with a lot of pores in them, and can start to understand if there's pore orientation, and if this can affect the seismic properties, which are S-wave anisotropy that we've seen in the lab in turning the core by incremental 45-degree increments. We find some variation in S-wave velocity. So this could be our anisotropic seismic velocity, and which isn't really seismically modeled at the moment. It's rather memory intensive, especially in pre-stack. But we reacted samples with CO2 in DI water, and we used DI to sort of maximize dissolution to understand what the end member, the dissolved end member is of the limestone. And we have these longer exposures right here, but I don't have the images from anything but this high porosity sample. And we also have an exposed 2-inch core that we have before and after velocity and permeability results for. So this is a registered volume of the before and after limestone before and after exposure, and the red is represents dissolved limestone. So we have some dissolution occurring all around the edge of the sample and inside of the sample too. And interestingly, we have a slight internal porosity increase, but a large pore surface area in decrease. So kinetically, we are dissolving away our reactive surface area and limiting the speed of the reaction as we lose pore surface area. So here's the P and S wave velocities. I'll zoom in to the P, and so after exposure, we actually had a gain of velocity in the low pressure regime, and as we increase, we end up dealing with limestone as the matrix. But it's interesting to see that maybe we're leaning on pore bound or crystal boundaries more quickly as we convert compliant porosity into stiff porosity. So here's just another map, and trying to quantify the compliant porosity where we're still a little bit too rough scale here. So we're still looking at dissolution pathways. So there's a dissolution pathway, and we ran permeability before and after on the 2-inch sample, and we're a little bit surprised to see that we lose permeability in a couple of these confining pressure levels. So maybe we need to think about if we stop injecting. When you start re-injecting, will you overpressure areas near the injection head? So that's just the rundown on some of the work we're doing in Pittsburgh, and so we're slowing reactivity by buffering with our solution and by losing reactive surface area, and we're actually losing some permeability too, even though we see some flow pathways opening up. And so this porosity change is to be fed back into a reservoir model to produce AVO response and 3D impedance volumes to understand the change in the reservoir for increments 100 200-year increments in the future. So thank you.
Any questions?
So the question is are we getting maybe internal reprecipitation of calcite? The experiment is designed to lose the ions out of the sample. It's suspended in a beaker. So we were trying to avoid reprecipitation. We can account for a lot of, well, we dried out the fluid waters, and we can account for a lot of the mass loss, but we could still have internal reprecipitation blocking.
Thank you. So this concludes this session. Let's thank all our speakers and thank you for your attention.